Oh, so you already hit the thing?
Yep.
Okay. So let's see. We've done the basics of angular momentum, and then we connected what we know about angular momentum to spherical coordinates. Now I have to tell you about something that's kind of puzzling, and it's that for mass 0, then the treatment I've been giving about angular momentum isn't quite right. Instead of 2j plus 1 states, one has 2, or let me just say there are 2. So, this is the case, of course, for the photon, and also for the graviton, and for any other for any other mass 0 particles. You all know this implicitly or explicitly because with the photon, you know there are 2 states of polarization. One can talk about the photons moving in the Z direction. You can say it's X polarization or Y polarization, or equivalently you can call it right circularly polarized or left circularly polarized, or some other combination. But in any case, you have 2 states, and the same is true for graviton. The reason for all this goes back to, and frankly this is sort of hard to understand, which is why I basically skipped it. The basic idea is to think about things relativistically and to imagine you have some standard Lorentz transformation that takes you from some reference state to a state of momentum p. Now, for a massive particle, the reference state is just the particle sitting there at the origin, not moving at all, and so then you boost it from that state up to a state of momentum p. Then you make some arbitrary Lorentz transformation on it. Now it has momentum lambda L, lambda p, and so now you do the inverse Lorentz transformation. And of the standard form, you see, with a Lorentz transformation that takes you from one frame to another, you've got a certain amount of arbitrariness in rotations. You can put in extra rotations, and so that's why this is a standard transformation set by convention. And this thing is called W. And, or actually it's W of lambda and P. I think if I get this right, I'm doing this somewhat from memory. And this thing is called the little group. And it turns out the little group is just SO3, the rotation group, if m is greater than 0. But it's something different if the mass is 0. Then the fiducial state is not the particle at rest. The fiducial state is the particle is the photon, say, moving along the z direction, and of course it's moving always at the speed of light. And so when one goes through this analysis, one doesn't find that the little group is SO3. One finds the little group is, if I'm not mistaken, ISO2, which is translation in a plane, and U1, basically. It's rotations in a circle. And it's the rotations in the circle, then, that give you the right circularly polarized or left circularly polarized. So I'm just mentioning that because, of course, it's physically very important, but the mathematics here, the only place I've ever seen that mathematics described is in Chapter 2 of Volume 1 of Weinberg's 3-volume treatise on quantum field theory. There may be other places where it's done equally well or more clearly, I don't know. Weinberg tends to produce the clearest description of anything. This stuff, I guess, needs to be sorted out a little bit more. But anyway, that's the story, and I don't think, maybe you guys have some questions. All right. Okay, well, remember I do have, oh, I forgot to bring the crackers. Let me. So I thought today we'd do addition of angular momenta. This is the part of angular momentum that tends to, I suppose, it's the part that frightens people the most. But I think I'm just going to go through the mathematics, and then I'll do 3 examples. And I think, or maybe one long example, maybe more than that. At any rate, so it should be clear. Now, let me ask you first of all a question. In 521, did you get taught about the direct product or the tensor product? In other words, these are things like this. Suppose you have an operator A that acts on states A, and an operator B that acts on states B, and now you can form something like this. You saw that in 521? Come on, I gotta know this. Yes, no, maybe?
Like, kind of indirectly. It wasn't specifically covering tensor notation, but...
All right. Well, the idea of this is simple, but it's a little bit strange, because normally when you're taught vector analysis, they just stick with, the teacher will stick with one system, and you get used to that. And so having 2 separate vector spaces becomes a little bit unfamiliar. But it's basically a simple idea, because then something like A plus B acting on some state, and let me call this, there are 2, one collapses this notation pretty quickly to finally just have AB. Okay, that's the standard thing that one does. But to keep it like this for a second, what this means, so let me just, this is equal to A on A cross B plus A cross B on B. So you just stay with this sort of schizophrenic notation, and you just let the operator A act on the states that it deals with, the operator B act on the states that it deals with, and that's all there is to it. So it's not that, it's not difficult. It's just it's just, if you've never handled it, it's unfamiliar. And an example of this, well, let's see, I don't want to, the subject that I'm about to start is intrinsically, it's an addition of angular momenta, and so clearly you have two systems, the angular momentum for system 1, the angular momentum for system 2, and so you have to use this notation. And I'm just a little worried that if I just start into the mathematics, if you haven't seen this for a while. It seems to me, though, that in Messier somewhere there must be a detailed description of this, because if there's one thing the French are good at, apart from sex and food and wine, it's mathematics. And so, and moreover, they also are very good at explaining mathematical things. And so I urge all of you, whether you saw this in 521 or not, to find the place in Messier, probably volume 1, somewhere in there, find the place where he describes this thing. It's sometimes called a tensor product. It's also sometimes called a direct product. And I'm not good at names, either for people or physical mathematical concepts, but or physical concepts. But it's one of these names, and it might be called composite systems. But in any event, I urge you to read that description, and it's probably a very clear description, and it'd be important because anything you do in the laboratory or in theory is going to involve, sooner or later, composite systems or tensor product, basically. All right, so what we're going to be talking about here is J1 and J2. And this comes up as soon as you discuss the hydrogen atom in any detail. That is to say, if you just are talking about the electron going around the proton, you ignore the spin of the electron, then you just have the orbital angular momentum of the electron. And then you just have one J. And I just use J as a generic angular momentum. But as soon as you get serious, then you have to say, well, this electron has spin. It has spin 1/2. And in fact, that's more angular momentum than you have in the ground state of hydrogen, where the orbital angular momentum is 0. And so you've got then two spins. You've got the orbital angular momentum, so this might be L for an electron, and this might be the spin angular momentum. And the total of these two would be the total angular momentum. And so that's what we're going to be talking about in general here, is adding two angular momenta together. And the question is, how do you go about that, and what's going on? Well, one set of states for this is the eigenvectors of J1 squared, J2 squared, J1z, and J2z. Whenever I say J2z, I think of a jacuzzi. Well, I've only been in a jacuzzi once at most, maybe, no, a few times, I guess, but it's not something that I grew up with. Anyway, the eigenstates of this are the things we already know about. Basically, this, we can write them like this: J1, J2, M1, M2, and these will be J1, M1, direct product or tensor product with J2, M2. And the deal, of course, is that J1 squared on J1, M1 is equal to H bar squared J1, J1 plus 1, J1, M1. And J1Z on J1 M1 will be H bar M1 J1 M1. And the same thing for J2 on these states. So J2 squared on J2 M2 H bar squared J2 J2 plus 1 J2 M2 and J2Z J2 M2 H bar M2 J2 M2. So those are the states. This is one set of states then that we are talking about, and we can also write this as J1 M1 J2 M2. This notation has the advantage of being reasonably succinct and clear. This is more succinct, and this is the conventional notation. The trouble is, when you look at this conventional notation, you sometimes don't know what the hell it is that's being represented here. And so this can be a somewhat confusing notation. It's not confusing if you have J1, J2, M1, M2, but if you have 3, 2, 1, 0, then you're not sure whether that refers to J1, J2, M1, M2, or to another description of this space. And this other description is in terms of the total angular momentum. And so let's go toward that total angular momentum a little bit slowly first. Let's notice that these eigenstates, these composite or direct product or tensor product eigenstates, are eigenstates of Jz, which is J1z plus J2z. And that's pretty clear from the nature of the tensor product here. Remember, I have chocolate and other sweets as rewards for questions. So you may ask questions, and you don't even have to be registered for the course to ask a question. All right, so let's just see what happens here. J Z on J1, J2, M1, M2 is J1Z plus J2Z on, and in fact, maybe I should write, you know, after saying all this to you, I almost think that we should abandon this conventional notation. This is the conventional notation. But this is almost as easy to write, and it is infinitely clearer. So I'm going to try to give this lecture in terms of the clearer notation. So, shall I do that, or is that be counterproductive? In other words, this is so what this thing is J1Z on J1 M1 times J2 M2 plus J1 M1 J2Z J2 M2. And this, of course, is H bar M1, and this one H bar M2 on J1 M1 J2 M2. So, in other words, this thing is the same thing as JZ on J1 M1 J2 M2. All right, is that clear? So that's how the direct product notation works.
J1Z is the sum of L1Z plus S1Z?
J1Z is the sum of J. Let me listen.
So
say it again.
J1Z is the sum of L1Z and S1Z?
It could be, but I'm not going there. I'm not going in that direction. Instead, what I'm saying is that J1Z might be LZ, and J2Z might be SZ. Okay, so I'm just thinking in terms of two systems. You're splitting it up into three systems. You're saying that J1 might be composited and also J2. I'm just taking J1 and J2 as two angular momenta. And as an example, J1 might be L, the orbital angular momentum, J2 might be S, but it's possible that we're not talking about that at all. We may be talking about two different particles, in which and we might be talking about the spins of the two different particles. So we might be combining a particle that has, so this might be the spin of one particle and this is the spin of the other particle. So it's just that both are angular momenta. And the point is, we know that if we have if we have one angular momentum, then these are the eigenstates of J1Z and J1 squared and J1Z, and these are the eigenstates of J2 squared and J2Z. We put them together in a direct product, and we see that we have eigenstates not only of J1 squared, J2 squared, J1Z, and J2Z, but also eigenstates of JZ, where JZ is J1Z plus J2Z. Okay? And the eigenvalues now are these. Is that all right? Okay, now these states are complete and orthonormal, and I can write them. I'm going to use this. I'm going to sort of switch over to this notation just because it's so much simpler. I mean, it's so much clearer. It's not simpler. It's actually more complicated. This inner product. Now, what is this inner product? Well, the inner product of states, something that I should have mentioned over here when I was giving my lightning review of tensor product notation. This thing is just this one with that one. And so this is simply delta M1 M1 prime delta M2 M2 prime. Okay? So these are orthonormal. And in the conventional notation, this thing is tracked. Okay, so these states here, which are written either like this or like that, are eigenstates of JZ, as well as of J1 squared, J2 squared, J1Z, and J2Z. Now, we're going to introduce other states now that are going to be eigenstates of J1 squared and J2 squared, but also of J squared and JZ. And so first of all, let's check that J equal to J1 plus J2 is an angular momentum. And what that means is, does it have the right commutation relations? And I'm just going to check the commutations of relations of J with itself. We want this to be I H bar sum on K epsilon I J K J K. That's what we want. Well, what do we have? Well, we know the J1I, J2J equals, what would that be? Right. This is 0 because the systems 1 and 2 have nothing to do with each other. So those commutators are 0. And so we take then Ji, Jj is J1I plus J2I, J1J plus J2J is equal to, well, J1 with J1I with J2J is 0, J2I with J1J is 0, so we just have to do this commutator and that one. So this is J1I, J1J plus J2I, J2J. And this, of course, then, let me take this up here. This is equal to then I H bar sum on K, and let me just say epsilon I J K, J1K plus epsilon I J K, J2K. Combining the two together, and that of course is I H bar sum on K, epsilon I J K, JK. So indeed, we have that J1, J2 is IH bar sum on K, epsilon I J K, JK. So the sum of J1 plus J2 gives us 3 operators that are angular momentum. They satisfy the commutation relations that we used a week ago or so to derive all those properties of angular momentum. And in particular, we know that J squared will commute with JZ. That's one of the relations. And another way of saying this is, since this is an angular momentum and since this is a scalar, the scalar doesn't change under rotation, so that commutator is 0. Any questions? All right. Now, I don't quite know where to write. J squared is J1 plus J2 squared. And this is going to be J1 squared plus J2 squared plus 2 J1 dot J2. And if I continue this up here, this is J1 squared plus J2 squared plus 2 J1Z J2Z plus 2 J1X J2X plus 2 J1Y J2Y. And we can rewrite that as J1 squared plus J2 squared plus 2 J1Z J2Z plus J1X plus I J1Y J2X minus I J2Y plus J1X minus I J1Y J2X plus I J2Y. Okay, so that's some arithmetic algebra there. And you remember we introduced J plus and J minus. And so what this tells us is j squared is equal to j1 squared plus j2 squared plus 2j1z j2z plus j1 plus j2 minus plus j1 minus j2 plus. Okay. Now, why did I do all that? I did all that because so far we have j squared commuting with jz, but now we see that j1, well, let me just say j squared, comma, j1 squared is 0. And why is that? Well, this would be j1 squared plus, well, forget about j2 squared because it commutes with j1 squared, which is system 1 and 2. Then we have all these other terms. And in these other terms, so let me see, I'm going to do it this way. This would be j1 squared with j1 squared, that's obviously 0. But then we have 2 j1z with j1 squared times j2z plus j1 plus commutated j1 squared times j2 minus plus j1 minus commutated j1 squared j2 plus. All of these are 0. This is 0 because it's a thing of itself. This is 0 because j1z generates rotations about the z-axis and j1 squared is scalar. This is 0 because both jx and jy commute with j1 squared and the same thing over here. So this thing is equal to 0. And the same thing can be said about j2, j squared with j2 squared. So now what we've got then are, we have the combined angular momentum, j1 plus j2, and j squared equals j1 plus j2 squared. We have that j squared commutes with jz being, of course, j1z plus j2z. And now we found that j1 squared and j2 squared also commute with j squared. And so now we have 4 commuting observables. J squared, jz, j1 squared, and this is supposed to be a comma. j2 squared. So these are 4 observables that all commute with each other. Okay, so that's what we've shown so far. And moreover, they're also all-dimension operators. So we have simultaneous eigenstates. And these simultaneous eigenstates are j1, j2, jm. This is the conventional way of writing it. And I think these equations will be clearer if we stick with the conventional way of writing these new states and the clear way of writing the states we started with. So these are eigenstates of j1 squared on this, of course, is h bar squared j1, j1 plus 1. j1, j2, jm, j2 squared, j1, j2, jm, h bar squared, j2, j2 plus 1, j1, j2, jm, and also j squared on j1, j2, jm. What is this? Chairs seem to be bosons in this end of the room here. Thank you. This is h bar squared, jj plus 1. J1, J2, Jm. And then we have Jz on J1, J2, Jm. And this is going to be H bar m, J1, J2, Jm. Okay. So this is what we know. This part here, these last two equations, come from the fact that we've just proven that J is an angular momentum. And the upper two equations come from the fact that we know what the eigenvalues of J1 squared and J2 squared are, because J1 and J2 are also angular momenta. And we also know that M is less than or equal to J and greater than or equal to minus J, because we proved that for any angular momentum, including this big J, which is the sum of J1 plus J2. All right. Any questions? Let me mention that, by the way, you don't need to take detailed notes, because these notes are online, although I use the conventional notation throughout. Let me just mention that it's not true that everything commutes, because, for example, J squared J1Z is not equal to 0. And, of course, J squared J2Z, therefore, is also 0. So you can't increase this set of 4 commuting observables. You can't increase it. Notice in both cases we have 4 commuting observables. Over here they are J1 squared, J2 squared, J1Z, and J2Z. Over there, J squared, Jz, J1 squared, and J2 squared. All right. So we now have two complete orthonormal sets of orthonormal states, 2 bases, J1, M1, J2, M2, also known as J1, J2, M1, M2. This is the conventional way of writing it, but I think this causes confusion. And the other one is J1, J2, Jm. So these are going to be the 2 sets of states. We have 2 different bases for our vector space. The vector space for the system of 2 angular momenta. And what we want to do is we want to see what the relations are between these vectors. And these relate, and we want to see a few more, we want to learn a few more things. So let me do the really important things that we need to learn first, and then I'll get to the inner products between these vectors. And between pairs of vectors, one from each basis, and these are the much feared coordinate coefficients. And they start out being tried with just the name Fletch, which is almost impossible to spell. Okay, well, let's look at what state has the highest value of Jz. Or what I mean is the highest eigenvalue of Jz, M H1. What would the state be? Well, in the first basis, it would clearly be the state J1, J1, J2, J2. In other words, you'd have the thing maximum spin up. Okay? So that's that one. And so we know then that Jz on J1, J1, J2, J2, in fact, is of course J1Z on J1 plus, whoops, times J2 plus J2Z. Oh. This stuff is a little bit tricky. You see why it is they don't teach it and they don't have to. And so this one is M, and it's not M at all. It's J1 H bar, J1, J2 plus J1, that's supposed to be 1. J1, J2 H bar, J2, J2. And so altogether this is H bar, J1 plus J2, J1, J2. Okay, so the state in the first basis that we started with, the state that has the highest eigenstate, all of these states, in other words, are clearly eigenstates of the composite Jz. The one with the highest value of M is the one I just wrote down, and the highest value then is J1 plus J2 times H1. So that's the highest eigenvalue of Jz for the composite system. Now, what state over here has the highest value? Well, this one, the state with the highest value of Jz in this other basis, J1, J2, Jm, this would be the state J1, J2, Jj. This has the highest, Jz eigenvalue. So we get that eigenvalue. Okay? The state in this basis with the highest value of Jz will be the state Jj. And so then what we learn then is that the highest value of J is equal to J1 plus J2. So what we've learned something sort of through the back door in a sense, that just by looking at the Jz values, we see that the composite angular momentum eigenvalue, the eigenvalue of J squared, the highest eigenvalue, it corresponds to the value J of J1 plus J2. Because if there were a higher one, we'd get a value of Jz that would be higher, and that would be a contradiction. So we know then that this set of states here has values. J1 and J2, by the way, are completely fixed throughout the whole lecture, for each system. What's going to vary is J and M, and we see the biggest value J can be is J1 plus J2. Question now is, what's the minimum value? And to figure that out, we'll suppose that the minimum value, but minimum eigenvalue, well, you know, the eigenvalue is really H bar squared J, J plus 1. So I'm just talking about the minimum parameter J0, or if you want H bar squared J0, J0 plus 1. So I want to find the minimum value of J0. Well, suppose it is J0. Then we know there will be two J0 plus 1 states of the form J1, J2, J0M. And again, we're, as usual, talking about a massive particle. It's a massless particle, which is two states. And then we have the next highest angular momentum, and we know that the possible values of angular momentum, you remember we showed, or at least of this quantum number J, were 0, 1/2, 1, 3/2, and so forth. They're half integer eigenvalues, and let's see, I slipped in here something that I guess I haven't explained. It didn't occur to me when I wrote the notes. The explanation may be a bit deep here. Well, the point is, so I'm doing this sort of as a hand wave here a little bit. In other words, suppose this J0, suppose it were 0. Well, how do we know that this one isn't 1/2? Why does it have to be 0 plus 1? The reason is that we don't expect our system to flip-flop between bosons and fermions. We're either dealing with bosons or we're dealing with fermions. And so if we're dealing with fermions, then this would be 1/2, this would be 3/2. And if we're dealing with bosons, this might be 0, this might be 1, or this might be 2, this might be 3, but we don't expect it to flip between bosons and fermions. So there are how many states here? Well, there are 2 J0 plus 1 states of that kind. And we go all the way up to the state J1, J2, J1 plus J2, J1 plus J2, and these then have 2 J1 plus J2 plus 1 states. Okay. So that's the total number of states. Now, there must be as many states in this basis as in this basis, and we know how many there are in this basis because we know there are 2 J1 plus 1 states here and 2 J1 plus 1, 2 J2 plus 1 states here. So the total number of states is 2 J1 plus 1 times 2 J2 plus 1. And so what we have then is that the sum from J equals J0 to J1 plus J2 of 2J plus 1 has to equal 2J1 plus 1 times 2J2 plus 1. So this is the number of states in the first basis, and this is the number of states in the second basis, where these states go from J1, J2, J0, and up to J1, J2, J1 plus J2. Okay. Now this sum here is the sum J equals 0 to J1 plus J2, 2J plus 1, minus the sum J equals 0 to J0 minus 1, 2J plus 1. And there's this famous theorem that was proven by one of those mathematical prodigies, the sum, when he was, I think, in grammar school, the sum of n from 0 to capital N is capital N over 2, n plus 1. And of course, the sum of 1 from 0 to n is just equal to n plus 1. All right. So we use those to figure out what this is, and what we get is that this is equal to 2 J1 plus J2 over 2 J1 plus J2 plus 1. So this 2 is that 2. And the sum of J is from 0 to J1 plus J2, J1 plus J2 over 2 times that. And then we subtract, I have to do then the sum on 1, and that is just J1 plus J2 plus 1. And now we're subtracting 2 over 2, J0 minus 1, because we're just going up to J0 minus 1, and then minus J0. So, our equation is this equals that. And the solution then is that J0 squared is equal to J1 plus J2, J1 plus J2 plus 1, plus J1 plus J2 plus 1, minus 2J1 plus 1, 2J2 plus 1. And that's equal to J1 squared plus J2 squared plus 2J1 J2 plus 2J1 plus 2J2 plus 1 minus 4J1 J2 minus 2J1 minus 2J2 minus 1. And altogether that is J1 minus J2 squared. So the minimum value of J0 is J1, which is the J0 due to the absolute value of J1 minus J2. It has to be positive, and so that's our result. And so now we have two bases, and we know what the states are. We have this set that we started with, and then we have this set where, of course, m is less than or equal to j, greater than or equal to minus j, and j is less than or equal to j1 plus j2, and greater than or equal to the absolute value of j1 minus j2. And it goes in steps of 1, as does m. So it stays within either bosons or fermions. I wonder if there's probably a tighter way of doing that argument, but I don't recall what that might be. All right, any questions? A couple of materials. All right, now, we know that both bases form the resolution of the identity operator. It could write like that, I guess. Anyway, one is sum m1 equal to minus j1 to j1. Sum m2 equal to minus j2, j2, j1, j2, m1, m2. Oh, that's the conventional notation. Well, let me write it both ways. That's the conventional notation. The problem with this notation is that it can be confusing. So let me rewrite this. That's the same thing, just written in a more clearer way. Okay, so that's the identity operator. It must then be true if we multiply from the right by a state from the second basis, namely J1, J2, Jm, that this is equal to this sum m1 equal to minus j1, j1, m2 equal to minus j2, j2, of j1, m1, j2, m2. Now, this inner product of j1, m1, J2, M2 with the state J1, J2, Jm. So this inner product here is between this state and this state. Okay. You see why people use the conventional notation, because in the conventional notation this would have been written J1, J2, M1, M2, and this would be J1, J2, Jm, and it's easy to buy that that's a nice simple inner product, whereas when you write it this way, the book is nice, but it's a lot clearer. Okay, now these numbers, which are these inner products, or equivalently these things are called the Clebsch Gordon coefficients. In fact, I spent so much effort spelling Clebsch correctly, but I may have misspelled Gordon. It's maybe an O. Okay. Does anybody know is it Gordon or Gordon? Probably Gordon. Use an O. Does anybody know? Gordon?
That looks right.
I expect that.
All right. Anyway, I'll have to get that one right. So these are the Clebsch-Gordon coefficients. Now, let's make an obvious observation here. These states over here, these new states that we're introducing, each one we can multiply by an arbitrary unimodular complex number, an arbitrary phase factor, and everything is perfectly consistent. And so there are at least two conventions for how you define these states. And the important thing is don't mix the conventions. So if you're in one convention, fine. If you're in the other convention, fine. You invent your own convention, fine. But don't mix conventions or you get into trouble. Now we can say something simple about these Clebsch. These things are called Clebsch's in the trade. Notice that, of course, 0 is Jz minus J1z minus J2z, because that's just the definition of Jz. So if we put this in between these vectors that make up the Clebsch, in other words, J1, M1, J2, M2, Jz minus J1z minus J2z, J1, J2, Jm, then this state is an obvious eigenstate for these two operators, and this state is an eigenstate for this operator. And so what we get here is H bar M minus M1 minus M2 times J1 M1 J2 M2 J1 J2 Jm. All right. So if this is not 0, when this is not 0, that has to be 0. And so that means that for all these Clebsch's, the thing is 0 unless M equals M1 plus M2. So this is the general rule for when the Clebsch's are non-zero. So that's clear. All right, now if we go beyond that and actually compute some of these Clebsch's, we get this recursion relation, which I'm going to have time to derive it, and I hope I'm going to have time to do at least a simple example. All right, the The basic rule that we're going to use for all of this is J plus minus on Jm, which we proved last time, is h bar square root J minus or plus m, J plus or minus m plus 1. And the plus 1 you can think of, you can put it there if you want, which is probably where it belongs. Anyway, on the state, J m plus or minus 1. So that's the basic rule that we learned a couple of periods ago. So what we're going to do then, and of course, as you know, J plus or minus is J1 plus or minus 5 J2. Okay. All right. So now we start out then with J plus or minus on J1, J2, Jm. So this is then h bar square root of J minus a plus m. And I'm going to write it this way because it's a little bit clearer. Whoops. Okay, so this is where we're using the full J, which is J1 plus J2, and that J plus minus, and that raises the lowers, and we get this factor. Okay. On the other hand, this thing is equal to J1 plus or minus plus J2 plus or minus acting on. Now we've got the right-hand side of this thing. In other words, we're applying J plus or minus to this state here, which is now expressed in terms of all of these states, these basic states that we started with, times these Clebsch's. And so this is the sum, and I'm just going to write it over M1, M2. I don't know why I used prime in the notes. There's no reason for that. So this is J1, M1, J2, M2, times these Clebsch's J1, M1, J2, M2 on J1, J2, Jm. Okay, so these guys are numbers. These are the Clebsch's, and these are the vectors here. And now these operators are going to hit these. And the way they do that is this is the sum on M1, M2, and of course M1 goes from minus J1 to plus J1, and similarly for M2. This is J1 plus or minus on J1, M1 times J2, M2 plus J1, M1, J2 plus or minus on J2, M2. All right. And what this is, again, using this rule, is, if we want, we can factor out the h bar. M1, sum over M1, M2, big parentheses, square root of J1 minus or plus M1, J1 plus 1, plus or minus M1, times J1, M1, J2. Whoops. Be careful. This is J1, M1 plus or minus 1. J2, M2 plus square root of J2 minus or plus M2, J2 plus 1 plus or minus M2. I'm almost getting dizzy here. J1, M1, J2, M2 plus or minus 1. And all of these guys are multiplied by the same pledge. Ooh, ooh, ooh. You guys should have said something to me. This thing here is multiplied by this pledge. Okay? Left out that pledge, and it sits over here. All right, so these are the Klebsches, and this is the equation. And now what you do is you take an inner product from the left with one of the basis states of this form, and bingo, you get a relationship among the Klebsches. So let's see, we've got 4 minutes to do that. Problem with space, though, as well as time. This is the relativistically covariant problem here. All right. Now I see why in my notes I use primes over everything, over all the n's. When we're going to take this inner product, we of course know that J1, M1, J2, M2, so imagine there are primes on all these m's, okay? Maybe what I should do is put primes on these guys. All right, let me put primes on these guys. On J1, M1, J2, M2, because it's delta M1 and 1 prime, delta M2 prime, M2. Now, that's fine for the top line. Well, the top line, actually, no, this is going to give us directly a Klebsch. But that rule, you see, that rule implies also that 0 is equal to J1 and 1 prime, J2 and 2 prime, J1 M1, J2, M2 is delta M1 prime, M1, delta M2 prime, M2 plus or minus 1. I'm transforming the primes and the unprimes. Oh, wait a minute, I'm sorry. This all right, I meant to write something different. So let me. this thing is going to be delta m1 prime, delta m1 prime, m1 plus or minus 1, delta m2 prime, m2. And similarly, so let me just see if I've got that right. Yeah, m1 prime has to be m1 plus or minus 1, m2 prime has to be m2, and the other one is 0 is j1 m1 prime, j2 m2 prime on j1 m1, j2 m2 plus or minus 1 is delta m1 prime m1, delta m2 prime m2 plus or minus 1. So those are the orthogonality relations that we expect, and they're clear and obvious. Now we have to apply them to here, and when we do...
Excuse me. So the equal zeros, that puts a requirement on what your n.
Say that again?
So you have that equal to 0.
Yes. That's
That's going to put a requirement on what your values of n1 and 2 are.
Right. When we take, what we're going to do is we're going to take an inner product of this equation. Remember, this equation is the following. It's the, let me use yellow chalk. It's that this thing here is equal to this thing here. You want chocolate or? Okay.
Chocolate side.
All right. So here's what we get, and I don't know where to write it because there's so little space. Maybe I'll go over here. What do you think? What is it? Actually, it's 46. Well, let me write it down since it's the last thing here. What we have, all right, I'm going to write it in its final form, which skips one equation. This will be saying the following: j minus or plus m, j plus 1 plus or minus m, and an h bar has to be canceled from both sides. j1 m1, j2 m2, j1 j2, j m plus or minus 1 is equal to square root of j1 plus 1 minus or plus m1, j1 plus or minus m1. I've also dropped the primes. j1 m1 minus or plus 1, j2 m2, j1 j2 jm plus square root of j2 plus 1 minus or plus m2, j2 plus or minus m2, j1 m1, j2 m2 minus or plus 1, j1 j2 jm. Okay, so this is a big recursion relation for these Clebsch's. So it relates three different Clebsch's to each other with these square roots. And with that, with these relations, you can figure everything out apart from these arbitrary phases, which one can then choose in a reasonable way. Next time, I'll do some examples for you. When I do the examples, you'll say, why did he make it so complicated on Monday? And so it'll become simple when you see the examples. I'm going to do the examples on Wednesday. And so that'll be that. So the homework, I gave in. I'm too much of a softie, but I gave in. So the homework, instead of being due Wednesday, it'll be due next Monday. But the next homework is due 2 weeks from this Wednesday. And I'll post them in a few days. Any questions? All right. Sorry it's so complicated. That's just the way it is.